Okay, so welcome everybody. My name is Nadia Carato. I'm happy to welcome you to today's workshop on estimating and correcting for measurement error using hidden Markov models by Paulina Pankowska. The Social Science Data Lab is an event series at the Mannheim Center for European Social Research. It provides a platform to present tools and methods for collection, management, analysis and visualization of data in the social sciences. Our speaker today is Paulina, an assistant professor at the sociology department at Utrecht University, specializing in data and methods quality. Today, Paulina will give an introduction to hidden Markov model and discuss how they can be used for measurement error correction. Oh, I'm still muted. No. Okay. Before we start, a quick disclaimer. We are recording this live stream in active speaker mode. Audio from on-site and remote participants will be recorded, and if your video is on while asking a question online, your video will be recorded as well. Okay, so the floor is yours. Thank you very much.
Hi, everyone. I'll just start by sharing the screen quickly, as I've been told. Yes. So maybe just before I start, I think it's nice to have it kind of interactive since it's a workshop. So just feel free to interrupt me if you have a clarification question or a more substantive question as well. We're a small group. I think there's 5 of us here and 5 online. So I think we can do that way. And also for the people online, just unmute yourself and interrupt me at any point, because it's more of a workshop type thing. So I would like you to just ask questions if you just are not sure about something or you have something to add. It would be nice to not wait all the way till the end. Yeah. So today I'll, as Nadia mentioned, introduce the idea of using hidden Markov models, latent variable modeling type, to estimate and correct for measurement error. And this is what I've been doing throughout my PhD. And I'm now continuing the work with Alex, who's here, on a project as well with Florian and Ruben. And actually, I'll talk a bit about the project more when I give an example of how to use those models. So just a quick overview. Is this on? I can also do it like that. So just a quick, sorry, the overview is not there. Okay, apparently the overview is not here, but it's supposed to be. I think something went wrong when downloading. But in terms of an overview, so I want to do, for those of you who are not more from like social sciences or not so familiar with the idea of what we mean by measurement error, I'll talk very briefly about that. So introduce the definition and then the implications of measurement error in data. Then I'll introduce hidden Markov models and kind of give an intuitive explanation how they work, what their main assumptions are. And then I'll talk about how we can use hidden Markov models in R. And here a disclaimer, I don't do it myself in R. I use a specialized software called Latent Gold because the functionality of R is still somewhat limited, especially if we want to do more sort of complicated model specifications. And so then I will finish by showing you very briefly how it looks like in Latent Gold, what I actually use, and why I actually then will become a bit clear why I actually use Latent Gold as opposed to R when we can do more realistic error scenarios, actually. But that's what was supposed to be on this slide. So just a quick definition for measurement error, as probably most of you know. So measurement error really occurs when we have the observed value of a certain variable and it is not a perfect representation of the true unobserved value of the variable or social phenomenon we're interested in. So for instance, what I did for my PhD is I looked at measurement error in employment contract type. So we have measurement error when truly a person has temporary employment contract, but in the data I use survey and register in either of those data sources, we actually have recorded permanent contract. And measurement error can be both random, so then it occurs without any pattern and is what we in data science at least refer to often as noise in the data. So it's just that, for instance, randomly by mistake, the wrong contract type is registered. But it can also be systematic, and then it occurs according to some specific pattern. So for instance, in my case, again, of the PhD research, we showed that sometimes for the survey, younger people are more likely to get confused and think that the informal agreement they get from their employer to be hired permanently is actually legally binding. So then they report having a permanent contract while they actually have a temporary contract, but they just have a promise from their employer to hire them permanently. So in this case, we would have a systematic error where there is a higher probability or chance of having error for younger rather than older people or for certain sectors. If that type of confusion, for instance, occurs more often in the health sector. What we focus on in this case for hidden Markov models is on categorical data, categorical longitudinal. But in this case, it's important because in categorical data, we often talk about misclassification, because what happens in measurement error is just we misclassify a temporary contract, for example, as a permanent contract in the observed data. And in terms of the effects, well, it can really severely bias estimates. So that's the sort of part, why should we care about this and try to do something about it? Measurement error can have strong biasing effects, been shown for different types of modeling techniques. And as a result, it can lead to incorrect research findings. And in most cases, we show that systematic error is worse than random error, because random error on average can cancel out, but systematic error does not. And so often, even though actually in some disciplines we only talk about random error, systematic error is considered to be more problematic, so we should pay more attention to it. And that will become also very important in the context of how we use hidden Markov models and model this systematic error. So again, just to give an example, in the research I did my PhD, we looked at actually specifically transitions between temporary and permanent contracts. And my PhD was funded by Statistics Netherlands, the official statistics institute or statistics institute of the Netherlands. And they were particularly interested in getting more accurate estimates of this transition rate, because it was actually used by policymakers to justify the flexibilization of the labor market. So the idea was that they're saying, no, it's great. You see so many people transition over the course of 3 months from temporary to permanent employment. It's what they call a stepping stone towards permanent employment, so our policies work. But actually what I showed in my research is that when we correct for the error, the transition rate at some point was 3 times lower than actually what is observed directly in the data, was I think particularly bad for the register data. And so it's not just about research finding, but in this case, it actually had also policy implications where we show that once we correct for measurement error, that is usually also specifically problematic for dynamic statistics, so over time statistics, such as transitions, then we get a very different picture about this whole idea of flexibilization of the labor market in the Netherlands to when we just take and treat the data as it is.
Sorry,
yeah,
that's a good question. Like the data source you did your PhD on, what was that, register data?
It was a combination of a register data from the population register and the tax authorities and the labor force survey. So we had overlapping information with the same people from the register and from the survey, longitudinal, yeah. And actually, we showed that the survey is slightly more accurate than the register. So people always complain about surveys, but actually there's a lot to be said that people know what's happening in their life and they can actually answer questions correctly. So just very briefly on sources of measurement error, just a couple of examples for surveys and then also for digital trace data. I thought it would be nicer with also more keeping in mind the audience, not to talk about register, but digital traces. So for survey, we have different cognitive processes that can affect responses, of course. We have recall bias. Sometimes we ask very difficult questions about how many times last year, 5 years ago, you did this and that. People just don't remember, or also social desirability bias. I'm now working with a PhD on also looking at pro-environmental behavior, and there a big problem is social desirability bias. And we get answers in surveys of how people would like to be and what their intentions are, than actually the type of behavior they're truly performing. And of course, we can also have poor questions or poor questionnaire design, and that can lead to misunderstanding. People don't really understand the question or they interpret it wrongly. And if we have very long, complicated surveys, questionnaires, then people also get tired. We have respondent fatigue, and then they answer just whatever, just to finish the survey as soon as possible. In terms of digital trace data, the biggest thing that's been increasingly talked about, and something we show also in our research that I mentioned with Alex, Florian, and Ruben, is that it's a big problem if we don't track all devices. So we have an incomplete data. If we, for instance, have someone's computer, but not their mobile phone, or vice versa, especially for what I will talk about later on in more detail, social media use, for instance, we just track people's computers, will be very inaccurate because most people use mobile phones when they go on social media. They also, with those tracking apps, people can temporarily switch them off. And that is also quite problematic because we see, or there's some evidence I've been reading, that people switch them off to save their battery, and that is then correlated with usage. So people who use their phones more are more likely to switch off the app potentially because they want to save their battery for other things. And then we have just incomplete data that can also be seen as a measurement error if we think about frequencies of usage, because we just have underestimation. Also, another thing is that we might have data that's not representative of individual usage. Parents often have their children use their tablets for games, use their smartphones for games as well. So actually that even though it's the parent's mobile phone, these type of frequency that we're recording and the usage we're recording is not necessarily done by them. So should be account. Yeah. So that's kind of a very brief introduction to what is measurement error, what's causing measurement error, and given the implications, it's important that we do something about it. And that's where hidden Markov models come in. So hidden Markov models are, as I mentioned already, latent class models. It's a group of latent class models that are applied specifically for categorical longitudinal data. They can also be applied not for measurement error correction. That's quite common. They are used in, for instance, actually demography type to look at life trajectories more and more often. So we just want to look at people's trajectories, and we have different data on their marriage and also on their children, whether they have children or not. We combine that into getting an overall kind of unobserved life trajectory or a situation in a specific time of life. But we can also use them to correct for measurement error. And specifically, we need to have longitudinal data. And in this case, the standard way is also categorical data. So we need to have, for a standard hidden Markov model, at least 3 time points to estimate it. Why they're quite attractive is that they don't require the data source to be error-free. So traditionally, normally, for instance, if we have a survey and we suspect there's measurement error there, we use registered data to benchmark this survey against, assuming that the registered data is error-free. What I showed in my research, rather flawed assumption. And so this is a very attractive alternative because we don't need to make this assumption. We can actually just use error-laden or data sources that contain error. And instead of using an error-free benchmark called standard data, they use repeated measure of one indicator, or extended hidden Markov models of multiple indicators. They extract information about the error directly from the data. So I will talk a little bit about the standard hidden Markov model, and then I'll show an example of an extension. So the standard hidden Markov model, to be identifiable, relies on 2 assumptions: the Markov assumption and the local independence assumption. So the Markov assumption is that any true state that we have, so if we continue with my example, any true contract type at time t, it only depends on the contract type, the true contract type at time t-1. So it's what we call autoregressive process of 1, of order 1. And then we have the local independence assumption, where we say that the observed state, so what we, for instance, register in the survey data, the contract type in the survey data, it only depends on the true contract type at the same time point. So if we look at these assumptions more mathematically and visually, that's kind of how we would visualize the path, what we call the hidden Markov model. And this here is the part that the Markov assumption relates to. So we see that here the true value of x, which is our latent variable. So the value of x in time 2 only depends on the value of x in time 1. And same here in 3, it only depends on 2. So we don't have arrows here between 1 and 3. So that's for the standard. If we do some extensions, we can also relax this assumption. Then for the local independence assumption, it's actually about this part. So we think these are the observed values, for instance, from the survey. Then the observed value in the survey only depends on the true value of this variable characteristics we're interested in at the same time. So that's why we don't have any arrows going from here to here or so on. This assumption is fairly problematic from a modeling perspective, because that means that actually we have an observed value that contains some error, but it's only depending on the true value. So that implies that then the error has to be random, because we see that the error that's included in the observed term is not dependent on anything else. And so with the standard HMMs that only have one indicator, for instance, survey or register or digital trace data, and only 3 time points, we cannot relax this assumption and we cannot model systematic error. So we cannot, maybe with covariates, sometimes would work, probably not, but especially what's very interesting often in longitudinal setups like that is to model error correlation. So that the probability of making an error, for instance, depends on whether an error was made previously, which for my PhD research was very important, because in the register data, they would provide monthly estimates of the contract type, but actually they were entered only once a year. So it's very likely that if the estimate in January was wrong, it would just be copied across wrongly, especially if no real change occurred throughout the whole year. And so we saw actually when we extended this hidden Markov model, the standard one, is that the probability of repeating the same error if no real change occurred was like 0.98 or something. So it's just extremely likely, and we cannot capture that if we just have a basic standard HMM, because we cannot model that. So then that brings me to my extension. Well, first let's like a bit of a summary what I mentioned. So we combine the Markov and the local independence assumption, and then we have the following probability of observing, for instance, a specific path in the survey data. So observing, if we talk about 3 only values of observing temporary, permanent contract in the data, in the survey data. So that depends on our initial state probabilities, what we call, and they are the probabilities at the beginning. So the probabilities at time 1 at the beginning of having temporary, permanent, or other contract, for instance. And that's time the transition probabilities. So that's the probability of transitioning from the initial state to a different state in 1, to a different state in 2, given the state in 1, and to a different state in 3, given the state in 2. And then we have the emission probabilities, or we also call them classification error probabilities. And those are related to the measurement part. That's the probability of observing specific value contract type in the survey, given that we have these initial state probabilities true, and then this true or latent transition probabilities. So that's kind of the 3 components of the hidden Markov models. And then in terms of extended HMMs, what I find most interesting is doing this multiple indicator HMMs, where we don't have only we have the true here chain, right, the true values, and they are not only dependent, we cannot only observe them in one data source, but in more than one data source, 2 in this case. Should be arrows here between them. I don't know what happened there. But this is what I did with this.
Sorry, my question regarding the previous slide. If you, generally the concept, thanks. Maybe this the other one with the X2. Just from an understanding perspective, if you say that X3 is just dependent on X2, how can you say that X3 is not dependent on X1, because X2 was also dependent on X1? So I'm thinking maybe from a DAG perspective.
Yeah. So it is dependent, but like through x2.
Oh.
So condition on x2
Okay.
that is dependent on x1 is no longer dependent on x1 separately in its own. But yes, in that sense, it's like this chain that depends because x3 depends on x2, which depends on x1 through x2, it does. But if we say x3 condition on x2, then it's independent on everything else that happened before.
Okay, thanks.
Yeah. And so if you come back here, so this is the extended two indicator HMM, and what's really, as I mentioned, attractive about this multiple indicator HMM is that they allow us to relax the local independence assumption. And that means that we can model more realistic error scenarios that also include systematic error. In this case, we didn't do I tried to do autocorrelation, but it didn't matter so much. Or maybe I can actually just introduce this whole model. So this is on a project we're currently working on, and we look at Facebook use frequency. We have a longitudinal survey from Germany. So this data that was collected for Ruben's project. In 3 time points, 3 waves of the survey, and we also have tracking app data from mobile phones, computers, or both. And we wanted to see how correctly or accurately Facebook use frequency is estimated in survey and digital trace data. Our idea for this paper was that, so I also had spent some time in a communication science department where everybody's like, well, all of our problems are solved now. You can use digital trace data. It's fantastic. It's recorded automatically. So there's just no error. So all these problems with surveys are now solved. And actually, increasingly, researchers use digital trace data to benchmark their surveys against. But then I started thinking a little bit about it, and I thought, well, it's fairly unrealistic. Maybe some problems of surveys can be solved by using digital traces, but they introduce new problems and data limitations. And so again, that's why we thought this setup or this modeling framework would be quite interesting because it allows us to model the error simultaneously in the survey and in the tracking app. And for this model to work, the only assumption we need is that the error in the first indicator, so in the tracking apps, is independent from the error in the surveys. And indeed, that seems like a realistic assumption because people answer a certain way in surveys, and there are problems with this, but I mentioned all these cognitive processes. But we could assume that those are independent of the problems that we have with like not tracking individuals, all of their devices. Of course, we can think of issues with that as well. Maybe people who are more privacy concerned both answer less accurately in the survey and don't allow all of their devices tracked. But that we would have to add a third indicator to be able to model then some relationships between 2 of the 3 indicators. But for now, we just assume that the errors in those 2 are independent. And what we've done here is we looked at the number of devices tracked, specifically if it's PC, mobile, or both. And that affected the error in the tracking app. And also we looked at later on also the number of devices an individual owns that actually Facebook could be used on. So also if people had tablets or smartwatches or so. Here we looked at other things. So we looked at survey wave. So we know people can learn, for instance, understand the survey better and maybe improve their responses over time. And we also looked at gender and age, since I found the literature that this can affect survey responses or accuracy. I actually, as I mentioned, tried to look at this autocorrelation, whether if we make a mistake here, it repeats it, but that was not highly actually influential. And I also was looking at whether we could add also covariates to what affects the transition probabilities, but that was not very important because actually these waves are only 2 weeks apart. So the probabilities of transitioning were so low. So people don't change the way they interact on Facebook and how frequently they use Facebook over the course of 2 weeks. So this was a fairly well-fitting model for what we were doing. So that's a little bit about HMMs. So it's a brief introduction. And now a little bit on how they can be used in R. So as I mentioned, I personally don't use R for this analysis specifically, but I've had a bit of a look around, and it seems there's quite a lot of packages that allow running some form of HMMs in R. They all, in my opinion, have their limitations. So quite a few of them, and if you're interested, by the way, so I put links here to the papers that were published about the packages and all the explanatory material, but they all have limitations. So often we cannot have multiple indicators. That's a problem. So we can only do this one indicator standard HMM, or we cannot add covariates. Also, a lot of it, so those are, by the way, models are quite often used in biology. And there they are more interested in continuous time processes. So they model diseases, and that it's kind of a continuous path of recovery, for instance. And so they don't have discrete time points, but they have a continuous underlying time frame. And that's slightly different. And then for some, apparently you could do it, but you need to write like the extension yourself. In some, we have to specify meaningful, what they say, starting values, which I find quite difficult because we don't really often know. I mean, it's already quite good if we know the nature of the error, so we can model the systematic part of the error, but it's very difficult to actually come up with starting values for the, well, transitions maybe, but for the especially measurement error probabilities. And also some cannot handle missing values, especially in the covariates if they already allow it. And what I find quite important is that they cannot properly use a three-step approach. And so what I mean here, if we go back to maybe the basic one, is that often we want to separate the methodological part from the substantive research we do after. So we correct for measurement error, we obtained more accurate, we'll never say error-free, but error-corrected data. And then we want to use this error-corrected data to do further analysis. So for instance, if we want to use Facebook Facebook use frequency as a predictor of political polarization or like belief in conspiracy theories, we want to correct for the measurement error and then use this error-corrected data as a predictor in further analysis. And that's normally, it's nice to separate the two and not to do it once. So we have the method part, we correct for measurement error, obtain this new error-corrected data, and then use it in the third step as the input into substantive analysis. But the problem is that those are probabilistic models. So we don't actually find that, for instance, individual one, according to what they answered, actually truly they have a temporary contract, a truly permanent contract. We get a probability of them having a specific type of contract. So what we get out of these models is we have a probability that, or maybe if I stick to this, we have a probability that someone is a frequent Facebook user of 0.8, but also a probability that they are semi-frequent Facebook user of 0.2. So basically the output of these models is probabilistic. It's not deterministic. Well, yeah, it's not deterministic, or at least we don't have 100% certainty that someone is frequent or infrequent. We have probabilities. And if we were to just use it as it's possible in R, we would just have to assign each individual to the category that they have the highest probability of belonging, and then we disregard this uncertainty. So we treat these estimates of the model as just data, raw data, and that leads to a lot of issues, of course, with, well, the standard errors, for instance, and the uncertainty. So we need to take that into account and account for this uncertainty. And in specialized software like M+, you might know, and Latent Gold, which is a bit more niche, there is a already implemented three-step approach where there is a correction factor for this uncertainty in the assignment of individual to classes. And so we run the analysis, we assign them to classes, we also store the uncertainty, and then we run the analysis, substantive analysis, while taking it into account and calculating the standard errors accordingly. So that's one, to me, a very important thing. And actually, in last few years, I see more and more research that they try to publish by just assigning it to the class without taking into account the uncertainty being actually criticized and rejected from publications. So that used to be what people did a lot, but more and more it's not really accepted. And of course, we can do that also in R manually. One way we could do that is to use a multiple imputation, and that's what I call it. Laura Buschoten did in the Methods and Statistics Department of Utrecht. You can do multiple imputation and then impute it with those probabilities, well, taking into account this probability. So there's ways around it, but there is no really implement solution in any of those packages. So if I go back to the packages, what I thought that one of the nicer packages, in my opinion, is still SecHMM. It has its limitations, but it does allow running a multiple indicator hidden Markov model. I think this LMS actually also allows it, and even allows inclusion of covariates, but it was a bit problematic when we wanted to include covariates in the emission probability, so in the measurement error probabilities. It just misbehaved, and it also doesn't allow including covariates in both the transition, so the latent part, transition probabilities, and the measurement part, so the emission probabilities. So, and it also provides no such intuitive estimates. So I chose to demonstrate with SecHMM because it has slightly more intuitive outputs, especially for illustrative kind of introductory purposes. So so with the SecHMM package, what I mentioned already, the project, that's kind of what I used as data. In this analysis, it was frequency of Facebook use in 3 time points, the free survey waves, and then we took the tracking app data and we matched it to the survey waves, more or less. So there was periods of 10 days around when the actual survey wave took place, and then there was another survey wave 2 weeks later, and it was like those 10 days around that moment when the survey took place, and the same for the 3rd time point. So then we have 3 time points that also, in terms of dates, correspond to each other, one from this survey indicator and one indicator from the tracking apps. And here what I initially did is I actually ran the analysis separately. So I used the survey data and the tracking data separately and ran 2 times a 1 indicator hidden Markov model to show you how bad it goes, basically, a little bit. And so if you see what we have in terms of the data is just 3 columns that correspond to the free survey wave and the matched time periods. And we have, it's like a 5-point Likert scale for the data that goes from highly frequent use to highly infrequent use. So people could say they use it several times a day, daily, weekly, monthly, and less than monthly. And we kind of, again, match the tracking data to those categories in the survey. It's a bit imperfect, but we did some robustness checks, and regardless how we exactly match the tracking data with the survey data, we get the same findings. So here I think we did, well, several times a day if we see usage every day more than once, daily if we see usage in these 10-day periods every day. I think weeklies we saw 1, 2, and monthly we saw, I think, once, and then less than monthly we didn't observe it at all. And then the first thing to do it when it comes to SecHMM, is to actually here, yes, that's the first line here, is we need to change our data into a SecDef type data or object. And so it's like designated as a sequence in R. And yeah, it's a very simple thing to do. And then we just say, okay, it starts at time point 1, and then we choose the columns that correspond to the sequence. So the 1st, 2nd, and 3rd column of the time period or the waves. And then the first thing we need to do when we run an HMM is to actually decide on the number of classes. And then for measurement error correction, sometimes we don't need to do it. So for instance, when I was talking about my PhD research, there it was very clear that we would have a model with 3 classes. because the 3 categories that were observed in the data, in the survey register, were actually true meaningful categories. So someone has temporary, permanent contract or any other type of contract. But with the Facebook frequency research is a little bit different because these 5 categories were just made up by us when we included them in the survey. So we just said, okay, we'll use a 5-point Likert scale, but we could have also used a 7-point Likert scale. That doesn't mean, it's just the way we ask the question. So it doesn't mean that these 5 categories we observe in the survey and in the matched tracking data are representative of true types of Facebook usage. We might have only 3 types, like maybe it's just frequent, semi-frequent, and infrequent, or we might have more. So in this case, we actually cannot just run a hidden Markov model with 5 classes, but it's better to just actually run various models with the number of classes going from, in this case, I chose 2. We don't want just 1, it's not very interesting analysis, all the way to 7. So we basically look at different specifications of the model, but just with regards to the number of latent classes. And then we use, well, officially 3 different criteria are recommended to select the model that's best fitting or most suitable. So we use, that's I guess one of the most important one, statistical model fit. We look at AIC, BIC, but also we're interested in class sizes sometimes. So if we have a very teeny tiny class, maybe that's just not really in class that's representative of a typology in the population, but it's just some byproduct of the data, or at least it's also maybe not important enough because it's not a very big class that represents a trend in our population. And also very important, we look at the interpretative value. So if we have a model fit that's, for instance, similar model fit in terms of BIC, AIC for 3 and 4 classes, there's not much of a difference. Then what I normally do is I look at the estimates of the 3 class, I look at the estimates of the 4 class, and I'm looking at whether that 4th added class is actually giving me any new insights in terms of a new typology, a new different, in this case, Facebook usage frequency. If not, if it just seems it's like a little bit artificially splitting 2 substantively very similar classes, then I go back to the simpler, more parsimonious solution of 3 classes. Yeah, so I did that twice. I adjusted, well, I put the data in the correct type object, and then I ran the models twice, once with survey indicator, once with the tracking data indicator, from looking at models with classes varying from 2 to 7. And then I just plotted the BIC. And that's what I get. So at least in terms of the number of classes, it's not so different. So here for the survey, it's quite clear that we have 4 classes. But for instance, here is this sort of a bit more vague situation that I just described, where actually 3 classes is also is the best solution, but 4 classes is also a very similarly well-fitting solution. So in reality, if I do this type of research, I would look at the output of both a 3-class specification and a 4-class specification, and I would see what I gained from actually using these 4 classes. What I do here is actually use both cases 4 classes because I want to show you how different the results are if we just use one indicator and assume by default that the measurement error that's contained is random in these indicators. So what I do then next in this case is I just run the model once again, but not with, I don't loop it with different number of classes, but I just specify the number of states to be 4. So the way this works, and I'll maybe explain more in detail, is first we build the model and then we fit the model. So first we specify and then we actually run the analysis. So for in this case, it's fairly simple for the standard one. We just specify the observations, which is the sequence data type we just created. and then we specify the number of classes. And for this case, that's enough to build the HMM because we don't include any covariates and so on. Then when we fit the model, what's quite nice in this package is that we can use random starting values, but we can also say use 5 different sets of random starting values. So that's quite important in order to make sure that we actually get a global maximum rather than a local. So it's very important to run it multiple times with different starting values, especially as the model gets more and more complicated, to make sure that it's converged properly. And in some packages it's not possible, but of course we can do it ourselves by looping around, just say, run it multiple times, and then just save all of the results. But this is a nice specific functionality of this package that allows us to do it automatically. And here I did the exact same thing, so nothing different here. I just used the tracking data instead of the survey data. So in terms of results, so what we get is we get what I find the more important or more meaningful results to interpret. We get these 3 components that I showed before: the initial state probabilities, the transition probabilities, and the emission or measurement probabilities. And just before we walk through them, I'll show you what we also get more technical outputs about, for instance, the number of iterations it took for the model to converge, the different best optimal solutions for the different starting values. So you see it should be 2, 3, 4, 5, 6. I think this is the best, and then actually these are all of them in a row. And then it just shows us what we actually did, for instance, here. So it just gives us some more technical output that's good to have a look at, but what we are actually interpreting is this. So here the initial state probabilities are also actually the sizes of the different typologies, or in this case, the different Facebook usage types at the beginning. So we see that it's actually quite reasonably well equally distributed for different. We have quite large classes for all 4 classes. And here we see the transition probabilities between the different classes, and overall what we see is the transitions are quite low. Maybe this one is not as low. So we don't really get much, if you go at the off diagonal, we don't actually get much transitions going on, which we expect, because basically we expect that people don't change their Facebook usage frequency so much over the course of 2 weeks. So what those probabilities tell us is, for instance, if we were in state 1 and we go to state 2, there's almost no chance to go from state 1 to state 2. But we could actually transition from state 4 to 2, or from state 4 to 1. So basically just shows us what is the chances of transitioning between different states over time. Yeah.
Just like the states are now no longer the 5-point frequency we had earlier, but they're kind of in between.
They are like the latent states. So actually, that's actually the most important part. Maybe I should have started with this. Those are the emission probabilities, and that's what we use. So those are the probabilities that tie the latent states that we were discovered in a way by or estimated by our model, and how they relate to the observed variables. And so we use this to interpret and make sense of our latent states. So we know that we have 4 latent states, but for now we don't know what they actually mean or represent. So we use this measurement probabilities, so the probabilities of how likely we are to observe, now we're looking at the survey, to observe this several times a day category, given that we are in state 1, for instance. Yep.
But in your theoretical construct, you're only collecting survey weights from 3 bases. So where does this stage 4 comes from?
No, this is not stage 4. Okay. This is actually the categories of each of those. So this has 4 categories, this has 4 categories, and this has 4 categories.
Okay.
So it's just the transition between these different categories. But when we talk about categories, we know the number of time points because that's specified by the data. But what we look when we do these estimates of different models with different number of classes or states is actually how many categories this latent
Okay.
variable has.
So it has something like a 4-point scale on like. how
Yes,
many you-
yes, exactly. So we say that actually Facebook use can be defined by 4 different types of use. And these are and in this standard, maybe also important to mention, even in this extended hidden Markov model, in this case for us, we assume that these probabilities are time constant. You can actually relax this assumption and have these probabilities depend on time, but we don't make it. And we also assume they're missing this transition probabilities to also be time constant. And that's why we get only one set of emission probabilities, because they are the same for time 1, time 2, and time 3. And here that's the same. The transition probabilities are the same for time 1, time 2, and time 3. So yeah. No. It's,
Can I ask one
yeah, of
question?
course.
Based on the result of like the emission probability and the transition probability, can we also infer anything from like how many categories should we design in future like research like surveys like
Yes,
more
you could
like
do that.
categories or will be better or like how is it possible to infer anything of that?
Yes, because actually if you so basically what we in this case say is that those represent real actual Facebook usage types. And so if we know that there are these 4 different Facebook usage types, then probably it's a bit of an overkill to have 5 different points. So indeed, you can use this, and that's quite common to use hidden Markov models to understand things that then can be applied in further survey research. So another way that is used is that we ask questions differently in a survey, then we use hidden Markov model to see which question has more measurement error, and then you don't use that question. That's another way, but it's just a very good idea. So basically, you see that at least if we trust this simple model, which we shouldn't, but that will be in a second, we have 4 different Facebook usage types. So there's no need to ask using a 5-point Likert scale, indeed. So if I go back, maybe to just have it into the actual basic one. So the latent initial state probabilities are actually the probabilities of the different categories that we have at the beginning. So it's this. It tells us at the beginning of our sequence what are the probabilities of X1 or people being in at one category. So like, let's say frequent use, infrequent use, highly frequent use, and so on. Then the transition probabilities I talked about, those are these probabilities. They're represented by this arrow. So those are what is the probability that if we were in state 1, 2, 3, or 4, or class 1, 2, or 3, or 4, they're equivalent terms, at least in this context. What is the probability that we will go to a different state in the next time point? Because these probabilities are the same as here. So these arrows are actually what's representing those latent transition probabilities. And then these arrows at the top are what's representing the emission probability. So given that we are in one of these 4 categories identified in X1, 2, or 3, what is the probability that we will observe one of the 5 categories in our survey data? And the number of categories, states, classes, we can call it different things. What we ran from 2 to 7, it's just about 4x, whether it's in time point 1, 2, or 3, doesn't matter, it's constant. How many categories should we consider? Yeah, is that clear now? How? Yeah, perfect. Yeah. So go back. So again, so that's what we see with the initial state probabilities. So the first thing that we found out from, maybe if we take a step back again, from this part is that we should consider most likely 4 categories. So we should consider that our latent variable, that in this case represents Facebook usage, have 4 different categories. So substantively speaking, we have 4 different user types, Facebook user types with regards to frequency, right? That's what we're thinking. And then what we find out next is how likely each person is to be in those different states, the probability of being in each state at the beginning of the sequence, and that corresponds to the class sizes also. So for instance, we see state 1 is the biggest state that most people, or the highest, not most, but the highest percentage of people are in state 1. But actually what we really need to focus on first is actually these emission probabilities, because we want to understand what state 1, 2, 3, and 4 actually represent. So here we see state 1 as a very, if we are in state 1, because it's conditional probability. So given that we are in state 1, it's extremely probable that we will answer in the survey that we use Facebook several times a day. It's a little bit less probable that we will, much less, not a little bit, much less probable that we'll say daily, and there's almost no probability that we'll sell anything else. So then I would label this state as frequent Facebook users, right? So this is how we make sense of the states, how we interpret them. Then we go to the second state. And so if we say these are frequent Facebook users, actually then we consider these. That's the measurement error, right? That's the people that actually are frequent state users, but reported to use it infrequently or very infrequently. So that's where we actually say, okay, these, but we see that it's fairly accurately measured in the survey, right? We have very little error. Then we look at the second state and we see that these are predominantly what I call semi-frequent users. And we have, still monthly users. So we could, if we kind of make this into a state that's weekly or monthly, then we actually can say, okay, these are semi-frequent users. And again, we have very little measurement error here, but then becomes a bit problematic because we have this overlap. So the way I interpreted them is that in state 2, we actually have this weekly, so semi-frequent users, and we have a little bit more measurement error because some are considered to be monthly. And instead, it's a little bit more difficult because these things are a bit ordinal, so they become a little bit vague. But if you have specific categories like I had in my labor market research, then it becomes very clear if it's temporary, and if it's permanent, then it's obviously an error. But here, I would still argue that, okay, these are semi-frequent users, and they're still estimated pretty accurately. And then here, what we see is those are infrequent users, and those are users that use it monthly or less. And again, they're quite accurately considered in the survey. Well, accurately reported or represented in the survey. And here it's interesting, we have this other class. Well, that's kind of still frequent users, but not as frequent. So we could call those highly frequent users and those just frequent users. So overall, what we get from this is that survey is doing a pretty good job at measuring Facebook usage. But the problem is that this model is based on this assumption that we only have random error in the survey data because it's this basic standard HMM. So then actually what's interesting is to add an additional data source and start modeling any error mechanisms that in a way we have to know about or have some suspicion, either from previous literature on like what type of errors are most common in this type of questions, survey questions, or what I did, for instance, my PhD research, I actually just sat down and talked to people who collected the data and who were in Statistics Netherlands responsible for this register data. And they said to me, like, these are the error mechanisms. We know that for the register data, some companies use a really inaccurate HR software, and those are the companies that actually there is some bug in the software and these things are registered incorrectly. So we actually could include that covariate because we knew which companies use this software to predict the error. And so it's also very useful to have some understanding of the data collection process and the errors associated with it to be able to model them here. Otherwise, I can try everything, but it's a bit of a gamble, I would say. And so here we get the estimates of the same basic model, but just using or standard model, the tracking data. And I didn't put the technical output because I think that's just the interesting part. So we see in terms of, well, you see already that the initial state probabilities are quite different. We have a very strong, much bigger state 3, so some category. And actually we have the fourth state that's quite small. So that's already quite interesting. In terms of transition, we also see a little bit more transition between the states. You see that these are a little bit lower. But the most, again, interesting is this one. So if we interpret the states again, we see that I start from this, this is state 2 that also corresponds to the highly frequent state. So that corresponds to, we go back here to state 1. So the order of the states is random, depends on the starting value. So that doesn't really matter. Then we have a state that is, daily, primarily some frequent, some weekly. So it's already a slightly different state that we saw in the survey. Then we have the highly infrequent. It's quite corresponding to also what we saw in the survey results. But then we have this other state that's, so these are highly frequent, these are somewhat less, but also still frequent. These are here semi-frequent, but rather also infrequent, and then really highly infrequent. So we have somewhat similar estimates, but they are not exactly corresponding between the two data sources, and especially when we look at the distributions. So what's really interesting, when we look at state 3, it has almost half of the observations. Think about it, the probability of being in state 3 is very high, and that's the probability of being an infrequent user. So almost, well, over 40%, almost half of our sample is in this infrequent user category according to tracking data, but in the survey data, that's this one, is 16%. So it's already giving us some weird indication that there's many more inactive or infrequent users according to the tracking data and the survey data. So we already get a bit of an implication something is going on. And that's when it's quite interesting to actually use an extended hidden Markov model to model these two things simultaneously. And that's what I did here. So in order to do that, in SEC-HMM, we just combine these two SEC data object, sequence data object using a list function together, and then nothing else changes. We just use this list as the observations or the data. When specifying the model, we then fit the model, and then again, we plot it. Well, in this case, it keeps kind of dropping. If we'd also do it beyond to 7 classes. I think 7 classes didn't actually even converge, so that's why we do not see it here. But we also can say, okay, 4 is a pretty adequate number of classes, or model specification with 4 classes is reasonable because we have this elbow here. So basically we see that as we go include additional classes in our model fit really improves. But then beyond 3, there's still improvement, but it kind of starts saturating. So that's why we use the elbow method, also very often using k-means. So we would still be okay with using a 4-class model, which as I did here as well. And again, it's the exact same thing. We just specify a 4-class model again to save the results. And then if we look here, and this is the most interesting, again, interpretive part to begin with. And here we kind of look at both what the tracking and the survey say simultaneously. So for instance, state 1 now is for both these infrequent, right? So here we see that they are infrequent users or highly infrequent users predominantly for both the survey and the register data. So we can say that state 1 for both, according to both data sources, is actually the infrequent Facebook users. And it's measured fairly accurately, I would say, in both sources. Then we look at, skip state 2, because that's the problematic one. We look at state 3, and we again see that here we have frequent, very frequent, also here very frequent Facebook users, but overall this could be a state or a class that's defined as frequent Facebook users, because everybody's using them at least daily. Well, not everybody, but the vast majority, right? The high probability. Here, state 4, we have, that's a bit of a more problematic one, but we could still say that these are people who are semi-frequent. Here it's very clear in the tracking data, but here it's a little bit inconsistency. But if we say they are daily or weekly, we still say there's some okay measurement. Again, because it's ordinal, there's some overlap. But what's really interesting from this analysis is this state 2. And that's actually, if you see 1/3 of all of our respondents in the sample, we think about the probabilities, they report themselves, the vast majority again, to use Facebook every day or even multiple times a day, but there is very little activity, if any, recorded in the tracking data. So this is like the most interesting finding of this analysis that we focused on in our paper, because this is really an indication that something goes terribly wrong in one of the sources or both. It's also possible, because it seems that there's such high inconsistencies. Those are people who are, it's not even possible to make sense what this, at least as things are now with this just 2 indicator model with no covariates, it's very difficult to make sense of this, because this is some true state that can only be defined as highly inconsistent for now, because if we believe the survey, it's highly frequent or frequent users of Facebook, and here we say that it's infrequent or highly infrequent users. So then in order to actually make sense of this, we have to extend our model further and try to look at how we can actually include predictors of errors that can give us a little bit more understanding of what's happening actually here. And of course, knowing the data generating process and understanding what's going on was very helpful in this case. So what we knew is that we have here people who are tracked on only their mobile phones, on only their computers, or both. And it's only like a third, I think, of all people tracked, or even less, that had both devices tracked. So we already started thinking here, knowing the way the data were collected, that there is high probability, or we had a hypothesis that something goes wrong with the tracking data, that the tracking data is not recording all of the activities because it has missing devices. So devices that are not tracked are actually the devices that people used Facebook the most on. So they are indeed frequent users, as suggested in the survey, potentially, but we're just not tracking the device that they use Facebook on.
So why did that specifically happen in stage 2 then? If some respondent didn't have like both device tracked,
Yeah.
this like issue happened across different states, but like, or yeah.
Yeah, so then because the tracking app was, we combined the data from all devices.
Mm-hmm.
So according to the tracking app, it was consistently in wave 1, 2, and 3 low. So this is not state 2 like wave 2, but this is just the second category of the latent variable.
Mm-hmm.
So basically the latent variable just, so yeah, so that's the thing that is a bit confusing in this analysis, but I was initially quite puzzled by it. So the state both represent, in this case, real Facebook usage patterns in terms of frequency, but they also represent a high inconsistency between the two sources that the model couldn't work out. So it was like, because the model basically just look at patterns of respondents, right? And then it looks for patterns, and then it identifies the states that correspond to these patterns. So it identified a state that correspond to frequent patterns in both sources, a state that corresponds to infrequent patterns, but then it just identified a state that corresponds to frequent patterns in one and infrequent in two. So there's just a group that has this type of observed data.
Okay. Maybe I don't know if I framed the question.
Yeah, go ahead.
Clearly, but I guess my question is, why did that happen specifically in state 2, but not like also in state 1, 3, and 4? Like, why does this?
Yeah, because basically it only happens to a subgroup of people. So it doesn't happen for all people. So it's basically, this happens for 1/3 of the observations. So for some people, we track consistently. So this is not a problem that is for the entire sample, but it's just a problem for the subsample that is included in this category.
Okay.
Does that make more sense?
Yeah, but why just this subgroup?
Yeah, because this is the group. Okay, so then maybe it will become clearer when I show the next results.
Yeah, of course.
And then if you still have the question, we go back to it. So basically, that's the problem with sec HMM, that this is kind of where the analysis would have to stop, because we cannot include covariates easily. So that's why now I switch to presenting this analysis similarly in like presenting the exact same analysis done similarly, but with covariates in latent gold. But maybe I still can answer that then now. So basically, once we included the covariance, we understood that this represents a category for people that were tracked primarily only on their computer. So basically, these are people in most cases that infrequent, it doesn't matter what they tracked on because they're infrequent. So then it's correctly tracked even on one devices. But this represents a specific typology of people that are tracked. They actually use Facebook often, but they are not tracked on all of their devices. So, and because that was or actually specifically what was even more the case, not both devices, but especially that they're only tracked on their computer and not also on mobile phone. And that was, more or less a third of the sample. So that's why if this was everybody, so if everybody was tracked only on their computer, then we would have those inconsistencies for all of the other states that also represent frequent usage.
Okay.
But this is like a combination of people that use in reality, in real life, Facebook fairly frequently, but were not tracked on their main device on which they use Facebook, which is mobile phone in this case, or at least, mobile phone and PC both, of course. And so, and that corresponds to about, 33% of the people.
Okay, thank you so much.
So then if I rerun this analysis in Latent Gold, here's a nice screenshot of how Latent Gold looks like. It doesn't have a beautiful user interface, I must say, it looks a bit old school, but it's a very powerful software specifically for latent variable modeling. It's incredible, especially for categorical. So I find the latent variable modeling is quite good for continuous data in R. So I teach a structural equation modeling course and we do it full in R, and that's quite good. But when it comes to, and then there we just use continuous data because it's more psychological, so a lot of Likert scales. When it comes to categorical, it's much better to use Latent Gold. You might have heard of M+, a bit bigger. That's also good. I don't like N+, so the personal level, I don't know, I just can't. So I don't use it, but Latent Gold is similar, and also the it's quite similar the way we specify things. The syntax is quite similar in Latent Gold and in M+, and if you use Lavan in R, that's also quite similar syntax. So you might be able to read this a little bit. Hope it's clear. So the first thing is options, and that's about the algorithms, what we want to have a tolerance, so in terms of convergence, doing the iterations when we accept a model as, we accept the convergence as all convergence criteria. So here we just, I don't play around with it because that's a pretty strict convergence criteria, but we want definitely the differences in the iterations to be very small. Here we can specify, that's quite nice. So it works, it has, it uses two algorithms, expectation maximization and then the Newton-Raphson. And expectation maximization is fast, but it's very good at like kind of going to the area where the global maximum will be, but it's not a very precise algorithm. That's why they implemented the Newton-Raphson as well. It's very slow, but the idea is that once we kind of zoom in on the area for the global maximum, it's really very precise at finding it. So basically we do 1,000, but then we have the convergence criterion. If it reaches it within the 1,000 beforehand, it then switches to Newton-Raphson, and then it finds the optimal solution. And here it's quite nice. If we have more complex models, we can change this around. I usually increase the EM iterations first to just get it a bit faster. And then if it doesn't work still, I also look at increasing the Newton-Raphson. Then here we also can specify starting values, the number of sets, and the number of iterations within each starting value. So it's quite a lot here. And that becomes quite important when we have more and more complex models, where it's very likely we're going to hit like boundary solutions and local maxima and so on. There's also this base criterion. This is an option implemented to avoid boundary solutions. Actually, here we can include all missing, so that's nice. It does well, it uses like full information, maximum likelihood, so it just uses the information that's there for the response, and for the covariate, it actually uses imputation methods. But we can have, thanks to that, missing values in the covariates and the response variables in both cases. And yeah, then we can also, if we want to do this 3-step approach and use the, as I mentioned before, the estimated classes and class membership further, we can just use this output option and then output a new data set, and here we specify basically what we want to include, the output, and what we want to keep in terms of the variables in the data set and so on. And here, this is the most important part, substantively, is where we specify our model. So here we specify the variables we want to use. We want the case ID, so the ID of the individual. Then the dependent are the response variables. So in our case, survey categories and the tracking Facebook usage categories. And then we specify if they are ordinal, nominal, or so categorical without order, or also we can do it with continuous in this case as well. Then the independent are the covariates that we use to predict the transitions or the initial state probabilities or the emission probabilities. And this here are like each line corresponds to the different component that I mentioned. Here we specify initial state probabilities. Here we specify transition probabilities. And here we specify the emission or measurement probabilities. And we have two equations here because one is for the first indicator, one for the second. So we know it's initial state probabilities because it's the zero, so it's at the initial state. So here we just don't include any covariates. So we just specify it as basically a model that's not based on any covariates. Here we just specify transition probability, they depend on the previous one. So we just maintain this Markov assumption. Here we actually specify that the emission probabilities are no longer random like they were before in the R example, but they actually depend, what I mentioned before, on the true, of course, so on the class, which is our latent variable, and then they depend also on, I said, yeah, gender, time or wave, and age. And here what's really important was for this analysis, we say, okay, the actually observed value also depends on which devices are tracked. And here, the mentioned, we also specify the latent variable, and we call it class option. This is some new function with the dynamic. It's a bit better, but this doesn't matter so much, actually. But we just say the class is a nominal because it's a categorical variable with 4 categories, yeah? So that's just our latent variable, is the true unobserved Facebook use frequency. Yeah. And once we specify it, we can run. You see this little play icon, that's what we press to run it. And we get quite a lot of output. But to kind of tie it back to what I showed you in the R output, I show you those probabilities again. And here again, we have the class sizes, the initial state probabilities, the transition probabilities here at the bottom. So these are quite similar to what we've seen already. We have very little transition between the different Facebook usage frequencies. And then again, the most important for us, the transition probabilities. And we see actually here the same pattern, right? So here in this case, it's just class 1. That's just slightly over 1/3 of the observations. But we see exactly what we saw before in the R output. We see that those are people that, I do this, are very unlikely to use Facebook frequently because they use it monthly or less than monthly, but it's very highly inconsistent with what we see in the survey, where it's very likely for them to use Facebook frequently according to the survey. Yeah? And here, for the rest, we see that the two sources rather agree, because here we see that they are frequent users, here we see that they are infrequent users, and here we see that they are somewhere in the middle. They're like semi-frequent, and yeah, here it's a bit less precisely estimated in the tracking data, but they seem to be actually semi-frequent. Yeah, and actually, I also ran it with free classes, and it gives us an even nicer solution where we see that they are frequent users, and that would be like this, frequent users here. And then we don't have this class, but we just have a third class where they are just rather infrequent user, which is less than monthly, monthly, and weekly. So actually this fourth class in this case is, I would say, redundant. But what's again most important from this analysis is that we have this high inconsistencies between the survey and the tracking. And what's nice in this analysis in Latent Gold is that we also used parameters to predict the probabilities of observing different categories in the tracking and the survey, but for the tracking is most interesting. So we see indeed that if we use just PC as the device that we are tracking, we're much more likely to observe that a less than monthly or monthly category in the tracking data. But actually, if we use both mobile and PC and we tracked both, we're much less likely to observe this infrequent categories in the tracking data. So basically, we're more likely to observe very little usage of Facebook if we're only tracking the PC. And this is effect coding rather than dummy coding. So these coefficients are not compared to a reference category, but they are compared to the sample overall average, right? So that's the, if you use effect coding. But so in this case, I use effect coding because it's a little bit more intuitive to understand it. So basically, tracking only PC will make us have a much higher probability of not observing much Facebook usage in the tracking data. But this is only sort of a first step and an indication that indeed we are just not tracking the right devices in this case, because it could be that actually those people that have only their PC tracked is actually also those people that don't use Facebook so frequently. So there could be that these two are correlated, and so we don't know that for sure. There's some indication, but there's no way of telling whether that's indeed the case. It could be that people who just don't use Facebook much, or just generally not very tech savvy or not so interested, and they're the ones that don't agree to have their mobile phone tracked, for instance. So that's what we did in order to really understand what's going on, or like to confirm more what's going on. We did this next step. So we did the analysis and the methodology, sort of the measurement part, where we actually found the classes. That's step one. Then when we talk about the three-step approach, step two is actually saving it here in the out file, the classification probability. So saving this classification of individual into different classes of Facebook use types. And then in step three, that's what we're doing here, we are running an analysis where we predict the class that people are based in. So in this case, it by default just calls it cluster rather than class, but that doesn't matter, it's the same thing. So we predict in which class or state out of the four we identified a person is in, based on a variety of characteristics, including, again, the device. So here what we want to see is whether the fact that we're tracking only the PC is statistically significantly associated with the probability of belonging to one of the four classes. So this is a multinomial logistic regression we're doing here. And what we see is in the parameters, indeed, that's the case, right? So we see that if we have both mobile and PC tracked, then people are less likely to belong to cluster one. So here there's a little bit more indication that actually just tracking both devices makes people less likely to belong to the inconsistent class that suggests that infrequent use according to the tracking and frequent use according to the survey. And what's also quite interesting, what's important, so basically there's a lot of evidence that the tracking data is the problem in that group, so that we have overall for 2/3 of our sample, fairly accurately registered or very accurately observed Facebook use frequency in both sources. But then it's going back to your question, for 1/3 of the sample, we have inconsistent usage observed in the two sources. But why the reason of this inconsistency, that's for 1/3 of the sample, we are underestimating Facebook usage in the tracking app because we're not tracking all devices. So that's basically how we then can interpret these 4 classes. So we have class 2, those are frequent Facebook users. Class 3, those are infrequent Facebook users. Class 4 is kind of semi-infrequent Facebook users. And class 1 are frequent Facebook users who are incorrectly tracked in the tracking apps, who are basically, these are frequent Facebook users who have missing information, I would call it, or like only partially observed information for the tracking data because we have missing devices. And what's really problematic is, in this case, is that if we also look at how the probabilities of belonging in each of those 4 clusters, whether they're affected by something like age or migration background, we see that there are effects, right? So we see that actually the overall significance of migration background or of age, for gender, no, but for those two, it actually affects the probability of belonging to the different classes. So what does that mean? That means that not only for 1/3 of the sample, if we just look at the tracking data, we have severely underestimated Facebook use. This sample is also not random. It's actually people who are different in terms of their age, for instance, from the average of the sample overall. So we have a group that almost self-selects itself into not giving us, not allowing us to track their information on mobile phones. And they are different people than the rest of the sample on average. So we're not just not tracking correctly information for 1/3 of the sample, but also those are people that are different age-wise. So then that will have an even stronger implication when we use tracking data to estimate Facebook usage and then use it in further analysis. Because it's not just that we have, well, sort of random error, but we have the systematic error where we're not tracking people fully or not tracking fully people's Facebook usage, and the people who we are not tracking fully are also, they have different socio-demographic characteristics than the rest of the sample. So it does seem that, for instance, in this case, it's more likely that the people are older, right? Because the probability with age, sorry, it's more likely that people are younger because the probability of being here with age decreases. Yes, okay. And so basically, the kind of take-home message from this analysis is that, okay, we cannot fully trust tracking data if we don't track all devices. And then there seems to be some form of self-selection into how many devices are tracked that is based on, or correlated at least with some individual level characteristic. So we have underestimation of Facebook usage for a certain group that is also different than the rest of the sample on average. So we expect the biasing effects to be even stronger here. And that's it, actually. So yeah, here we can also look at it in terms of probabilities rather than in terms of parameter estimates. But the concluding remarks is that HMMs can be a powerful tool to correct for measurement error, but they can be difficult to use. So for instance, with R, it doesn't seem that there's a comprehensive package to do, for instance, what I wanted to do with this analysis. And then in order to really model this, the error processes correctly, it's really important to understand and to know the data generating process. So for instance, this with the tracking app was something that Ruben was like, maybe, you know, we didn't track everybody, all of the devices. And so it became quite obvious kind of avenue to explore. But it is important to have an understanding of what's going on in order to be able to also model it correctly. And now I'm done. So I guess, we have 3 minutes for questions. a lot of information, but yeah. Sort of, there's something in the chat. You can have a look. Oh, thanks a lot. Okay. Perfect. Oh, yeah, you said. Okay. Well, if there are no questions, but if you are interested, you can always contact me. Or yeah, hopefully the paper's under review. Hopefully it'll be out soon. So yeah, that's it.
Hey, so thank you very much for your excellent talk. Yeah, before we say goodbye, the social data lab will be back on October 18th with an input talk by Jack Collins on neural networks. And yeah, thank you, everybody.
Thank you.